eigenvalues and eigenvectors. Sometimes also called as latent values and latent vectors. Sometimes also called as characteristic values and characteristic vectors. All same. Okay? Eigen, latent, characteristic, all same. Now, there is something called as eigenvalue problem. There is a problem in mathematics which is also called as eigenvalue problem. What exactly it is? Suppose if we have a square matrix A, for a given square matrix A, if I can find non-zero vectors capital X's such that Ax equal to lambda x. Let me repeat. If you can find for a given square matrix, if you can find non-zero vectors capital X's such that Ax equal to lambda x for some scalars lambda. Such a problem we call it as a eigenvalue problem. Eigen is a problem basically. It's a problem defined in mathematics. Okay. That problem tells me for any given square matrix, if you can find capital X's vectors in such a way that Ax equal to lambda x for some scalars lambda, such problem is called eigenvalue problem. Okay. Now the point here is I am talking about non-zero vectors capital X. Zero vectors for any value of lambda x equal to 0 is always a solution. Okay. In fact, this can also be written as a minus lambda I into x equal to 0, which looks in the form of homogeneous system of linear equations. Remember, homogeneous system of linear equations, which is always consistent, which always has a trivial solution, which is x equal to 0. So the question is always about what would be those non-trivial solutions x's such that this matrix into x equal to 0. Okay. So if you are able to find all those non-trivial solutions, then the problem is called as eigenvalue problem. Okay. Now, when do we have non-trivial solutions for this? Suppose if you have a system Ax equal to 0, okay, this has a unique solution which is a trivial solution when the rank of the matrix equal to the number of unknowns. Since A is a square matrix, you are going to have, suppose it's an nth order square matrix, n by n matrix, then you are going to have n unknowns, n equations, n unknowns. Okay, it will have a unique solution when the rank of the matrix A equal to number of unknowns equal to n, which will have unique solution which is a trivial solution. When do we have non-trivial solution? When the rank of the matrix A is less than n. When do it will be less than n? When the determinant of the matrix A equal to 0. That means if in this scenario the non-trivial solutions, that is non-zero solutions, are possible when determinant of A minus lambda I equal to, this gives us an nth degree polynomial in terms of lambda, also called as characteristic equation. Are you getting how we approach this determinant of A minus lambda equal to 0? I am looking for non-zero solutions. Zero solution anyway would be there because it's a homogeneous system. Always you have a trivial solution. I am looking for those non-trivial solutions which are possible out of this entire system of homogeneous equations. Okay, in which case I should have determinant of A minus lambda equal to 0, which gives me the characteristic equation. Okay, this characteristic equation is always an nth degree polynomial in terms of lambda, which will have n roots. By fundamental theorem of algebra, an nth degree polynomial will always have n roots, may be real or imaginary. So this is going to have n roots, that means lambda equal to lambda 1, lambda 2 up to lambda n. Getting that? Now, for each lambda that I am going to take, suppose lambda 1 Ax equal to lambda 1 x. This gives me a homogeneous system. Understand? This gives me a homogeneous system, but a particular value of lambda 1. Lambda 1 I have given a specific value. Out of n roots I have taken one of them. 0, 1, 2, 3, 4, 5, whatever it can be. Okay. This gives me a homogeneous system, n unknowns. Okay. After substituting the value of lambda 1, I may get non-trivial solutions. That's the reason why I got lambda 1. Why did I get lambda 1? Because I am going to get non-trivial solutions. All these non-trivial solutions will be a solution space. Getting that? That means if I substitute lambda 1, this is going to give me x1 solution space. So for lambda 1, I got x1 solution space. Okay? All these vectors, in fact, all these lambdas, we call them as characteristic values or latent values or eigenvalues. All these lambdas, characteristic values, latent values or eigenvalues. For each corresponding lambda, I am going to get a subspace itself. Is it or not? A subspace itself. It's not just one vector. X1 is not, capital X1 is not just one vector. You are going to get a set of vectors which forms a subspace. I think we have already shown that one, right? Which forms a subspace. It's not just one vector, I am telling you again. It's not just one vector. If you remember my graduation or your graduation, I think most of the teachers would have told you for every lambda 1 you would have found out only one vector. Even I have found only one vector in my graduation, but it's not like that. That one vector is just a basis vector in that entire vector space. Okay? So this gives me a subspace of a vector space of vectors. For another lambda 2, I am going to get x2. These vector spaces, each of the vector, we call them as eigenvectors. And eigenvectors will be there for a specific eigenvalue only for the given matrix. Given the matrix A, for the specific value of lambda, you are going to have those specific excess vectors called as eigenvectors, latent vectors or characteristic vectors. Are you getting that? So for each lambda, you are going to have a eigenspace altogether. We'll have an eigenspace. Getting that? This entire system, in fact, what we call it as eigenvalue problem. If you are able to find all those capital X's eigenvectors for specific values of eigenvalues lambdas, non-zero eigenvectors, such that Ax equal to lambda x is called eigenvalue problem.